Hello and welcome to Live from the Lab. This is the show where we look at different technologies that Brooker has developed to help scientists explore the world around us. Today's topic is X-ray diffraction. In particular, diffraction using a two-dimensional detector. Now, two-dimensional detectors have been around for a fairly long period of time, but recently we've seen quite an increase in them in general use instruments. This is because these two-dimensional detectors have gotten to the point that they can actually be used as both zero and one-dimensional detectors also. So really you can have one tool to do all the different jobs. I remember when I first used a two-dimensional detector. Back before joining Brooker, I actually looked at thin films. And in those thin films you'd want to grow a certain phase in a certain direction. Very, very well-aligned direction. In fact, they call them an epitaxial film. Now, though our best efforts were to grow that single phase, oftentimes we may actually grow a few different phases in the film, especially when we started growth. With conventional diffractometer having a limited window into reciprocal space, we would only see certain phases, but we never quite could understand what was going on with our materials. Once we started using a two-dimensional diffractometer, our eyes literally were opened to these other phases. We were able to see them, to understand their orientation relative to the main phases, and then reduce and remove them using different growth conditions. Today, we're going to go over some additional examples. We're also going to talk about the technology. So we're going to start by talking with one of the original innovators, Bob He. Then we're going to head over to our application labs and see some of this in action, both in terms of the software and the methods, but also how the hardware is implemented. And then we're going to answer some of your live questions coming in on the stream. So with that, let's get on with the show. I'm now joined by my colleague, Bob He, one of the innovators of two-dimensional diffraction. Hi, Bob.
Hi, John.
So two-dimensional diffraction, it's kind of a fairly old technique. I mean, when I think all the way back to the first X-ray images, from say Lowy, they were actually 2D, right?
Oh yes, they were 2D image. Yes.
So why did 2D go away?
Because the old time when you do 2D, you need a film. You have to. It's very expensive, and also at that time there's no much technology available to treat the 2D detector. You just treat it like an image. But later on, when the point detector, like a scintillation counter, proportional counter is developed, and you can get many information which you, for example, for face identification, that's sufficient. Or at that time, it's for the limited technology, that's good enough. So people have been using that for a long time.
So in your opinion then, what do you think was the thing which really allowed 2D to come back?
I think there are two things. First is available of those two-dimensional detector. What I mean is real two-dimensional detector when you can record an X-ray like in the image. So it's like a pixel with a certain pixel. And also the computing power. When you have a computing power, because for two-dimensional information, there are always much more information needed to be processed. So in that sense, we have these two technology available, then the two-dimensional diffraction come back again. Yeah.
And how long ago do you think that was?
We could count it back to like 30 years ago.
Okay, so about 30 years ago. Now,
yes.
In terms of that detector technology, what kind of technology was being used in the two-dimensional detectors at that time?
And I think there were like an image plate, but for us, the most advanced was high star multi-wire detector. Yeah, it's a gas detector. And since that one, we first used that detector for like a single crystal structural biology research. Then later on, we realized that it's a very good tool for analyze the powder diffraction data too.
So I know when I first saw a two-dimensional diffraction image, it was really eye-opening. I mean, and it might sound cliche, but it was like I was seeing all kinds of extra information that I'd never seen before. I was used to seeing just these diffractograms being peaks and, on a little line chart. But all of a sudden, it's like my eyes opened and I could see that image and see the Debye rings and such. What was your first reaction when you saw, say, a powder or something like this on one of these 2D detectors?
Yeah, before I saw 2D, the modern 2D diffraction image, I used the conventional point detector for many, many years. It's even from my PhD work. But since I saw the 2D detectors, I found, that's amazing because we have so many information available. We can do much better job for powder diffraction and also have many new applications to be developed.
And one of your roles here at Brooker then was to help to develop this technology and move it forward. So after those wire detectors, what was that next step in the two-dimensional detector hardware?
Hardware is you mean the detector hardware, or you mean all kind of hardware?
Yeah. Say the detector technology.
Okay. You mean after high star available, right?
Yeah. After the high star with the multi-wire, what was that? What was the next technology?
Oh, the next technology. Okay. Next technology is the we call the we saw the one tech technology. That's more like trade name, but its reality is based on a resistive anode. So it's like a multi-wire detector without wire. We call it a gas detector because we have this patented resistive anode. So we can control the resistance of the anode. So we can make sure the X-ray signal is catched only for the interested X-ray energy. So only those energy can discharge the gas in the detector.
Okay, so in those original wire detectors, what was happening is the X-rays would come in, they would hit the gas, create electrons. Those electrons were detected by a grid. The new technology, the electrons would come, hit this resistive anode, and then be read out by a delay line sensor, right?
Oh, yes.
Okay.
Because you don't have those wire anymore, so you can achieve much higher counting rate and also resolution.
Okay, so better resolution, better counting rate. That was kind of,
yes.
Okay. And now things have changed quite a bit again, right? Now there's a new technology out there.
Yeah, we in the recent past 10 years, we gradually switched to the pixel detector, like our Agar 2 detector. Those detector has much better counting rate, and especially resolution and also the spatial correction. Because in the old gas detector, you always have some kind of distortion and images, so you have to do a spatial correction. But for the new detector, it's based on semiconductor technology. The pixels are so precise, talking about nanometer precision. So then you have much better, more accurate, and two-dimensional diffraction information.
So now in these detectors, there is no counting gas, you mentioned, right?
No, in the new detector, we don't use counting gas anyway. It's a direct conversion from the X-ray to the electrons, so we can read out. Yeah, especially now we have those new hybrid pixel detector. Yeah.
I know personally when I was working with some of these detectors in the lab, moving from, say, the high star to the Vantech and then finally to the Eiger, it really felt like a quality of life increase. I mean, no spatials meant that we didn't have to collect those corrections. I can move the detector to optimize resolution and coverage, and also just, it just kind of works, right? When it's solid state, you just turn it on and it's going to work.
Yeah, it's much more reliable. Yeah, it's for the old detector, you have to worry about the gas or the other. Especially high star, you have to regassing every few years, and you have to calibrate the detector. You take about more time to calibrate the detector than the collect data. But for the new detector, you don't have to do all kind of these things.
Right. And don't get me wrong here. I mean, the old technology was great at the time. Just as new technology became available, really has increased the ability to use these detectors in a wider variety of systems.
Yeah, exactly. Actually, the old detector and helped us develop many of these algorithms. So basically, many of these fundamental equations, all the computer software to treat this, to process this 2D data. We learned a lot from those the previous generation technology. Yeah.
And I think that's one of the things that sometimes is overlooked. I mean, oftentimes we look at the hardware of something, but that algorithms and the methodology in the background is something that we don't think about so often. But I know you've done a lot of work on that method development also, right?
Oh yeah, yeah. Actually, I think that's probably more important. But yeah, of course, to most users, you first impression would be from the hardware performance. But we have a big team basically doing the software development, the algorithm, doing all the tests. So to customer, you basically you just directly work on your software, but there are many things already done in the background.
And Bob, I certainly know that you have some great talks out there on YouTube. You also have a book available, right, which goes into the depth in terms of the algorithms and the science behind a lot of these methods.
Oh yeah, yeah. That's like basically like a notebook for myself, so I can remember everything I was done, and also easy for me to talk to users. And eventually, I developed into a textbook, and it's quite useful, especially for me.
Yeah. So another transition I guess I saw in the solution level of things was it used to be that you had a dedicated two-dimensional diffractometer, and then you might have a dedicated, say, powder diffractometer. But nowadays, the 2D detectors are actually more of just a general tool found on most instruments.
Oh yeah, that's previous is like limited by technology. We have a special requirement for two-dimensional for the actually optics for two-dimensional detector, and also the two detector is also has a limitation like gas detector. But since we have those pixel detector, we have those new technology. We can collect 0D, 1D, 2D with one detector. Just switch it. So in that case, also some new development in the X-ray optics, for example, like MUS, all those things. We can have one instrument which can do 0D, 1D, 2D, all these applications.
So of all the different applications, which ones do you feel like benefit most from having access to a two-dimensional detector?
I think the user, because different user may appreciate different part, but I think the three application benefited most from two-dimensional detectors. The first is the stress, so we can measure stress much faster, more accurate. Especially with 2D detector, you have large angular coverage, so you can collect residual stress data without actually tilt the sample, which is very useful, especially for recently, for example, people working with thin film or coatings. You won't have low angle, two-theta angle available. So in that case, it's very sensitive to the sample position. So in that case, if we have a detector which can measure large angular range without actually tilt the sample during data collection, we can improve the precision much more, very significantly improve the precision. That's for stress. For texture, and since you collect several diffraction rings with large gamma range, so you can collect the texture much faster. This can be very significant. Yeah, and also third is like a grain size, or we call crystallized size measurement, because you have the information along the diffraction ring. If you see a spottiness of the diffraction ring, you know that's large crystal size. Then you can, based on the information, you can actually measure the crystal size. These are three application most benefit from 2D detector.
Yeah. I think in general too, we could probably say that microdiffraction.
Oh yeah.
Really
I think
benefits.
yeah, exactly. Actually, but the microdiffraction is because microdiffraction could be a face ID, can also
Yep.
do other information. Yeah, microdiffraction, that's definitely a big benefit too. Yes.
Yeah, so
also
in all of these techniques, right, the universal point is that it's really decreasing measurement time, but it's also increasing the amount of accessible information that we have, right?
Oh, yes, yes, yes. And because you see all the information simultaneously, which make a big difference, it's not sometimes not the time. For example,
Hmm.
if you do an in situ measurement, you want to see all the diffraction range in the 2 theta range, in the gamma range. You basically want to see what's going on with the instrument, with the sample during like the heating or some chemical reaction or charge discharge. So in that case, the 2D detector is must.
Are there any measurements where you would actually prefer not to use a 2D detector, or that you would use a different detector, like a 0D or a 1D?
There are many because there are many methods already developed based on point detector, and also there's some limitation. For example, you have like thin film attachment, the parallel beam geometry to control the sample roughness. In those cases, you want detect to be a point detector, and also you do like a structural refinement. You want to get a very high resolution, 2 theta resolution. In this case, with point detector, you can really control your like slit size. You control the many X-ray optics. You put many device, and then you can. In that case, the point detector would have an advantage. But fortunately, our new 2D detector can also be a zero detector, 0 dimensional or to 1 dimensional or 2 dimensional detector.
And that's one of those really, I think, important changes in the X-ray diffraction solutions recently has been that these detectors now have a 0D mode, a 1D mode, a 2D mode, very easily to access with the users, right?
Oh yeah, that's a big benefit. You can have one instrument for all. So you don't have to have a dedicated 2-dimensional diffraction information. Yeah.
Right. I mean, right tool, right job, definitely.
Oh yeah, yeah, yeah.
Yeah. So to see this in action, what we're going to do now is we're going to actually head over to the lab, and we're going to see the software. We're also going to see some of the hardware. So thanks for joining us, Bob, though.
Oh, thank you, John.
All right, and we'll talk to you in the future.
Okay, talk to you later. Bye-bye.
Hi everyone, today we're in the Materials Research Lab and we are here with the D8 Discover. So we're talking about 2D today, and so we've got our Eiger-2 detector here. This is the 500K. Do want to point out a couple of other components on this. So we have our trio optics here on the primary side. These are 3 distinct beam paths. Really convenient because you have the access to not only a line focus, but also a global mirror, which you combined here with a collimator. So the collimator, of course, very important to create a little spot beam. Anytime you're doing a 2D type of scan, you would want to have a nice little spot beam. So these are nice. They're magnetically mounted, very easy, no tools. We pop them back on. You know that they're going to be aligned every time. So after we have created our spot beam with these collimators, we've got our stage in the center. We're going to be working on a texture experiment today. So it's very important that we're able to turn our sample, we're able to spin it in the phi direction, and we're able to tilt it in the chi, or the psi direction. So we've got our sample right here mounted up. We're looking at a little steel part today. This is on our centricularing cradle. So lots of degrees of freedom here. We've got X and Y motion, we've got Z motion, and then we have our ability to rotate and tilt our sample. On top of that, we have our laser video. So laser video, very important for positioning. When you have any sort of non-uniform part sizes, it's very good to be able to say, you know, I want to make sure that sample is right in the middle of my instrument. So you need to be able to adjust things like X, Y, and Z. So we can use the laser video to really control fine-tuning of positioning. And we'll see that on the software here in a second. Finally, on the back end, we have our Eiger detector. So this is a 2D, 1D, and 0D detector. We're going to be operating it in 2D today. So notice I have it oriented this way. So the aspect ratio is wider than it is tall. So the wider part of that is going to allow us, whenever we're doing our debirings, to get much larger sections of that. Very critical whenever you're doing a texture experiment, because you might have some extra intensity at not right in the center of your debiring. So very good to be able to measure further along that Debye ring whenever you're doing a 2D experiment. So, all right, so with that, we're going to close the door. We'll switch over to the computer. All right. Okay, so if you see on my computer now, we have this camera interface. So this is the laser video, which is nice because it's fully integrated into the software. If I turn on one of the lasers, you can see a nice bright little red spot. So that's on top of that's pointing down off of the laser video interface. And so where that laser is lined up with the crosshairs, that's where the center of the sphere of confusion is. So we know that that spot right there is going to be what the X-ray beam is hitting. And so if I were to do something like want to move over to the left or to the right, or top or bottom, I can simply drive around until I find a position that seems of interest. Yeah. So for this particular piece, I want to make sure I'm like kind of right in the center. Right about there sounds good. I've got the Z already dialed in, but same thing, you could drive Z up or down, and you would see that laser move to indicate that you're not quite at the right height. So same thing that you would do for any other experiment. I'm going to do a quick scan real quick just to see where are my peaks of interest, because we'll assume that I haven't looked at this material before. So I'm setting a start and stop range. We're going to do some steps. You'll notice I'm doing a coupled 2 theta scan. So this is going to move my tube and my detector at exactly the same angle. And that's one of the really unique things about the Eiger 2 detector is that even though it is a 2D detector, historically, for some of the older generations of 2D detectors, you would need to take the frame and then drive the detector, and then take another frame and drive the detector, and take the frame and drive another detector. And then you would stitch all of these together, right? And that's where you started to run into some potentials for errors, is whenever you're stitching these images together, right at the edge, maybe there were some inaccuracies in terms of merging these frames together. If you've ever done anything with, say, PowerPoint, or if you've done any sort of photo editing, you understand that sometimes corrections lead to, a little bit interesting things. So with the Eiger 2 detector, what we're able to do is what's called a continuous scanning 2D frame. So the whole thing comes out as one frame, and we just continue to drive the detector up, 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 up. And so mathematically, what we're doing is we're driving every pixel through every point in the scan. Which of course adds up to a lot of computing powers whenever you're trying to handle all of this. But thankfully, all the integration has been done, so it's just a seamlessly integrated process. What you end up getting here on the screen is we see just one continuous frame coming in, right? So this will be a single frame. There's no post-processing in terms of like stitching things together or making sure that you're importing them in the right order. It just comes off as a single frame. All right, so we can see our first peak coming in right here, right? That's a nice, nice sort of even peak. So I can tell that this is going to be somewhat finer grained. Nice little Debye rings here. And then as it continues to scan, you will see other Debye rings coming in. Right? So coupled scanning 2D diffraction, very, very cool stuff. If for no other reason than just the ease of use. Right? So once we start looking at this data, we're able to look at the integrated data back down to 1D. You can do this in real time. You don't have to wait for your scan to finish. And we can see, yep, we've got some interesting diffraction peaks coming in here, a couple of strong ones. We happen to know that this is a piece of metal, so it's going to be a higher symmetry. But if I say I'm looking for a peak right here around, say, 51 degrees, we've got another one here around 40, 43-ish. I can start going ahead and planning my texture experiment. So when we start planning our texture experiment, we're going to want to know where our useful pieces of information are. So I'm going to go over to our wizard, and I'm actually going to start a new one. I'm going to go to texture. All right. And I'm going to use that information about where my peaks of interest are. And I'm going to say, I want to go to a texture scan. And I know that I'm looking for a peak around, what do we say? We were looking around 43. Got another one around 51. So I'm going to go back in. I'm going to say, I want to scan something at 43 degrees 2 theta. All right. So it will automatically calculate both my 2 theta and my omega. So that's half of my 2 theta. I can say maybe we'll take, I don't know, maybe 5 seconds per frame. And then we're going to start using this interface down below to plan out our texture experiment. So what we're doing in a texture experiment is we're going to take our sample with our normal direction pointing out, and we're going to rotate it in phi. Okay? Then we're going to tilt it, and then we're going to continue to rotate it at one tilt. Then we're going to tilt it, and we're going to rotate it at another tilt. And what we're doing is if we have a specific normal direction, one set of planes that are very oriented, say, in this direction, we're going to point them in a direction that is controlled by the cradle. And what this will allow us to do is generate this overlay where we can determine which direction relative to the sample surface do we have more or less of these planes pointing. So it basically gives you a sort of a map of which direction you see enhancement or preferred orientation or texture, depending on whether you're talking to a material scientist or a powder person. So historically, what you would do is you would say, what tilt ranges do I want to do? Maybe we'll go, say, 15 to, say, 60. And you would do, if we see here on the screen, all these little dots. Historically, these dots would indicate one specific data point. And we would basically need to fill in this grid with data points to illustrate which direction we're pointing that sample surface. So we would need to do something like that. And we would need to fill in this whole range with data points in order to create that map. Now, with the 2D detector, what's really cool is that you don't actually need to take all of these extra pieces of data because the coverage is so wide. It's such a large active area. So if we go to this coverage 2D detector, you can see what areas are actually covered by that very large detector. And you can see here we've got some green lines and some red lines to sort of indicate what coverage we can see. And quite obviously, it's a lot of redundant data. So what we're able to do is get away with, say, much fewer frames because we're covering these long segments. So maybe we'll do, say, so we wanted to do, say, 1545. We could do, say, 2. And you see it dynamically updates to indicate how much of the that sphere you're covering. And so here, if we go from, say, 15 to 45 psi, we can cover this just in 2 separate frames. So one at 15, one at 45, and we're able to fully fill in this map. This is going to be right now about a 7-minute pull figure, which is really remarkably fast. Final point of this is if you do have this large coverage, one of the neat things you can do is if we go back to Commander, we can see here that we've got 2 peaks that are right on top of each other. So at this distance with the detector, about 150, 170 millimeters from the sample, we're getting about 11 degrees of coverage in tooth data at any one moment. So what that means is we could actually park our detector right in the middle of these 2 peaks and say, I want to go from, we'll park it at 48, right in the middle of that. If we park it at 48 instead, okay, what we can see is that we're actually able to cover all of this and get 2 pull figures, which further increases your speed of data collection because you're getting quite a bit of data all at once. So that's it for our texture experiments. Thanks for hanging out today. We're going to head back over to the studio to answer some questions that you might have.
Hi, and thanks for coming back to the studio here. And what we're going to do now is ask your questions. Now, if we don't get to your questions, then you can always send them in to live.events@brooker.com. And it looks like we've had quite a few questions come in. So thanks for sending them in, and continue to send them in while we're answering. So the first question is from Andrea, and that is PDF and SACs in relation to the 2D detector. So I think probably the question is, can it be used, and is it useful? And actually, I can take this off since I'm the only one up here. So the answer to that would be it can be used for both PDF and SACs. So a detector like the Eiger uses a silicon sensor, so it can be used for things like moly. And because it has such a large open active area to it, you actually gain back any losses that you lose due to, say, transmission of the beam through the sensor. One other thing to note is that the Eiger is compatible with those radiations, so you don't have to worry about radiation damage with it. Now, in terms of the PDF measurement, The gain that we've found, or the best configuration I should say, that we found to use is actually to put your sample into a capillary tube in the center of the instrument, then use a line-focused beam off something like a global mirror, or even better, a focusing mirror. Focus that beam onto the detector face, and then use a detector actually in a one-dimensional mode. And because that Eiger detector is so large, you're going to get huge gains in terms of your scanning time. Something like 2 times faster, say, than a lynx eye detector or conventional 1D detector. So that's how I'd probably recommend using it for PDF. Now for SACs, we'd use it in full 2D mode. There is, a detector like the Eiger. It has basically no limit to its dynamic range. So you could actually use it without a beam stop. The only downside to doing that is that you may get excess beam scatter. And what that comes from is that transmitted beam makes it through the sample, and then it's going to hit air and then scatter, and then that's going to create some background. So because of that, we would actually still recommend using a beam stop, just because it's going to give you a little bit better background in terms of your measurement. Now the next question, that's from Mark, and that says, can a system be upgraded with the Eiger? And the answer to that is yes, as long as it's one of our newer instruments. So there's a D8 Advance and a D8 Discover. This would be our kind of medium-sized cabinet, and then the larger cabinet. And the units that are upgradable are the ones that came out, say, around 2009 and newer. And they kind of have more of a square shape to them. So if your instrument has the doors, that sometimes we call them accordion doors, they have like 4 pieces to the door, and you'd open it up. That one, unfortunately, is not compatible with the Eiger, but the new one with the sliding doors, or the Advance with the one swinging door, that unit could be upgraded with the Eiger. Next question from Gokay. Is there any ideal setup for pole figure measurements in terms of tilting and rotating the sample, also to reduce shadowing? Absolutely. So when you are doing pole figure measurement, you are going to want to use a tool like the Wizard. That's going to help for planning that 2-dimensional coverage. And this is actually not trivial, because the coverage along the ring, we call that gamma space. And the reason we call it gamma and not chi or psi is because it's actually a planar detector intersecting that spherical reciprocal space. And because of that, depending on where the ring hits, if it's hitting near the edge or near the center, and depending on the offside of the incident and the outgoing angle, that's going to change your coverage. And so that's why it's very important to use a planning tool like the Wizard. So what you would do is combine that with something like a cradle, where you can tilt the sample without the sample moving out of the center, and that's going to give you the best result for pole figures. Now when we're doing texture, there are 2 types of texture that people look at. You could be looking at kind of microtexture, that is texture of a very specific area of the sample, or texture of an overall sample. Since the grain size in some metals can be fairly large, sometimes we recommend actually oscillating the sample in X and Y while you're doing the texture to make sure that you're going to get a good distribution of the different grains and not just single crystallites themselves. So that would be one other tip for pole figures. In terms of reducing shadowing, that's something also that would be graphically shown right in the Wizard. So to reduce shadow and stuff like that during the planning stage, definitely look into the Wizard. It's a great, easy-to-use tool. Next question from Becky. I have a Vantec 500. Can that be used for 0D and 1D modes? Unfortunately, Becky, the Vantec 500 is only for 2-dimensional measurements. In that case, you could pair it with something like a lynx eye detector. You could take the Vantec off, put the lynx eye on when you want to use it, and then swap it back. This is something that is easier on the newer systems, the ones that come from the last 10 years. But it's possible on all of our systems to be able to swap detectors. The reason behind that, though, is that the Eiger detectors, they actually are a pixel-based detector. And so there we can actually address individual pixels themselves and then bin it down to that 0D and 1D modes. But in that case, if you have a newer machine, you could also upgrade that Vantec 500 to an Eiger detector. We have another question from Andrea. And that question is this new detector the Eiger 2R? Yes, Becky. Or Andrea, excuse me. That is the detector that we were looking at today. So there's actually 2 versions of it, though. There's the Eiger 2R 500K, which has been out for a while. And that detector sensor has 500,000 pixels, and it's kind of rectangular in shape. The Eiger 2R 250K, that was recently released, and that one has a little bit smaller sensor. So it has 250,000 pixels. I believe it's 40 millimeters by 40 millimeters in size in terms of its active area. And it's great for systems where you want to have some 2D capability, but you don't need that maximum size of the 500K. All right, next question from Dan. My 1D detector says it can be used to measure 2D. How does that work? Well, 1D detector has sensitivity across it. If it was like my phone here, it would have, say, strips just in one dimension, not in the two dimensions. And normally when the strips are oriented like so. So the beam is coming in, comes off as a line, and then we're going to scan it, and that's how you create your one dimension. Well, what you can do is if you reduce the beam to a point, so now you're hitting that center and creating the cone for 2D diffraction, you could take your detector and spin it this way. So now the strips are going this way. We place a small slit in front of it, and now when we scan it, we can actually build up the two-dimensional image. So that's one way to create a two-dimensional image using a one-dimensional detector. Another new way that we've actually come up with in the last few years is something called Bragg 2D. In that case, you don't have to actually reduce the beam down to a spot. What we do instead is we use the full divergent beam from Bragg-Brentano. So it comes in, diverges towards the sample, then it'll come into the detector and hit. Now what we do in order to create a 2D image is we simply map out then the different pixels on the surface of the detector itself. And as we're scanning it, we keep that information. And when we plot it out, we can actually create a two-dimensional image which corresponds to the tilt of the grains along the goniometer direction rather than transverse to the goniometer direction. So this will give you very similar information that you would get to a traditional 2D scan, but the benefit of having a very large footprint on the sample itself. And there is an application note available for that called Bragg 2D. So check that out on our website. Next question from Goke. Actually, quite a few questions. What is better in primary optics, polycap or global mirror? Can we use point focus with the global mirror? It's actually a very, very good question. And I would extend that to something called a Montel mirror also. So when we look at creating a point, you can create a point beam in many ways. One way would be that you start with a point focus tube, and you simply stick a few apertures in front of it, say 2 pinholes. That's going to reduce that beam down to a point. But even though it's spatially reduced as it leaves the collimator tip, it still has some divergence to it. It's going to grow, and it's going to get a little bit bigger. Generally, in this case, the beam is probably going to be about twice the size of your collimators. So if you're using a 1 millimeter and a 1 millimeter, by the time it hits the sample, it's probably going to be about a 2 millimeter spot. So it's not the most efficient in terms of conditioning the beam, but it is very cost effective and easy to set up. Now, if we go to a global mirror, what that is going to do, it's a planar device. So it harnesses the beam. It's a mirror, and it takes that line beam and takes it from being a diverging beam to a parallel beam. So now you have a parallel beam that's very, very parallel in one direction, but in the other direction it's still divergent. So when we put 2 pinholes or 1 pinhole in place, what you're going to see is that that beam still diverges along the line focus of the beam. So that's going to give you more of an oval shape on the sample. Now going to a polycap, that has a symmetric divergence. So what a polycap is, it's basically a bundle of capillary fibers. And that bundle has a taper on the incidence side, so it's going to pull in all those spot-focused beam. It's going to come out as a nice spot, normally about 2 millimeters in diameter. It's a divergence of about 0.1 degrees in all dimensions. And now we can cut that down, and it's going to give you a fairly good spot on the sample itself, fairly bright. Now the downside to this is that it's going to have all of the X-rays in it because we're just using capillary to refocus. So we're not going to, say, get rid of the K beta or any of that white radiation in the beam. So to overcome that, what you could do is use actually a special optic for spot beam called a Montel optic. What a Montel optic is, it's actually 2 mirrors that are glued to each other. And the beam is going to come in, strike one surface, bounce off, then strike the other surface, and come out very straight in both dimensions. And because it's a mirror, because we're relying on a diffracting event off of the surfaces, that's actually going to give you some purity in the beam. going to have K alpha 1, K alpha 2 only. Going to get rid of that white radiation. And the divergence of the beam is very small, in the order of about 0.05 by 0.05 degrees. So very, very straight. That means that you only need a single aperture after this mirror. It's going to give you a great spot size on the surface and actually very, very good brilliance. In fact, we connect this Montel mirror often with our microfocus sources, which run only at 50 watts, very low power. But because that Montel mirror is so good at harnessing a large number of those photons, it's going to give you excellent brilliance in a 2 millimeter spot size. All right, so keep the questions coming, by the way. So we have another question that came in from, sorry if I mispronounce, but Kathavath. What is the advantage of 2D phaser and XRD shown recently in a demo? Well, I'm guessing by 2D phaser, what you mean is actually seeing 2D diffraction from our benchtop, the D2 phaser. So the D2 phaser is a small benchtop instrument. And up to now, you've only been able to do either zero-dimensional or one-dimensional diffraction, where you just get that trace. Now, when you get the trace, you kind of have to trust that your sample preparation was perfect. You have to trust that you have a small grained powder, that it's randomly oriented, that you have no packing defects, that you don't have any big clunkers type crystals in there. They're giving you sharp diffracting peaks. And that's not always the case. You know, we always do our best, but that's not always the case, that we don't have those defects. Well, if you use 2D, you can actually do this Bragg 2D scan, large footprint on the sample, and looking at the uniformity of the line is going to tell you if that sample is a perfect powder, or if you have spots, it's going to tell you that you have large grains in there. If you see that you have streaks, say bright spots kind of coalescing in one area, it'll tell you of preferred orientation. So you can go back, re-prepare that sample, get a better result. So that's a benefit of using 2D in something like a benchtop. Another question from Gokay, what is a good collimator size for texture analysis? Well, there is a duality in texture analysis between resolution and information. So what I mean by that is that if you use a smaller collimator, you're going to get better resolution, both spatially on the sample, but also you're going to see sharper peaks in the 2D data. By using a larger collimator, you're going to sample a larger area of the sample, but then the peaks themselves on the detector face are going to be wider, so you're going to lose resolution. So what I like to do is I like to use the largest collimator I can while still separating the peaks of interest on the detector face. So if you have two peaks that are very close to each other, you're going to have to use a smaller collimator, perhaps something like a 0.5 millimeter or even a 0.3 millimeter. On the other hand, if your peaks are well separated, go for as much flux as you can, go for a 1 millimeter, and that's going to give you very nice data because you're going to sample more of the sample itself. All right, next question from Andrea. Are there any secondary beam side optics recommended needed to use with the Eiger 2? I guess no slits are recommended. Well, Andrea, there are actually. When you're using it in a 2D mode, we do have beam paths which are evacuated, so we call it the evacuated beam path. And those are kind of nice for reducing any sort of background that you're going to have. By actually sucking out that air from the secondary beam path, you're going to remove all that air scatter, so it gives you cleaner background. So that's one thing that you could use in a 2D mode. But then if you're going to use that Eiger 2D detector for 0D or 1D, there are also optics for that. Everything ranging from parallel plate style collimators, sometimes we call that an axial or an equatorial solar. Those are used for grazing incidence diffraction type measurements or in plane diffraction type measurements. There's also an analyzer crystal that is actually in a component called a Pathfinder Plus, and that's used for doing very, very high-end, ultra high resolution X-ray diffraction on thin films. So it's a whole number of different optics that you can place in front of it, but you are right, for 2D, you know, a lot of times we just use the whole thing, just unedited, use the whole detector. Next question from Andrea. For microdiffraction using a snout collimator and XY stage, if the snout is 0.3 millimeters, the spot size on the sample would be more than 0.3 millimeters. It depends on the optic that comes before that snout. So generally you're going to have your beam, or your tube, Then you're going to have some sort of a conditioning optic. Then you're going to have the snout. Now that conditioning optic, it could be everything from, well, like nothing. Like we said, you could have a point focus beam just going through the snout. In that case, generally, your spot size is going to be about twice your snout size. So 0.3, probably about 0.6. It's due to the divergence of the beam through it. If, on the other hand, you have a Goble mirror there, then that's going to be a line focus tube, flat Goble mirror. That's going to produce a beam that is a flat line, very straight in one direction, but fully divergent in the other. We typically pair that with a pinhole and a snout. Still going to lead to a beam that in the one direction, so in the direction of the straight beam, let's say left to right, it's going to be about 0.3 millimeters, but in the other direction, again, about twice as much, so say 0.6 millimeters. If you're using the Montel optic, on the other hand there, so that would be a point focus tube or a micro focus source with that Montel optic, which is the two Goble mirrors side by side, that snout size, 0.3 millimeters, that's going to be the size that you're going to get on the surface. So there you'll get 0.3. Next question from Zhaodong. Can Eiger-2 and a cradle do wide-range reciprocal space mapping? Absolutely. There's actually a wonderful app note that I put together on that. The way that I would use the Eiger-2 in that case is in a one-dimensional detector way. So I'd use it as a 1D detector, fully open, and I'd actually probably even narrow it down in this dimension. You know, it doesn't have to be as tall because it only has to be as tall as your beam. So it's 40 millimeters tall. It only has to be about, say, 10 or 15 millimeters to capture the full beam coming off the sample. That's going to help with any sort of background. But the Eiger is great for this application because it's never going to saturate. So when you capture your substrate reflections and you capture your peak reflections in the same scan as it's going, they're all going to be linear. So no worry about the substrate, say, saturating the detector locally. So the Eiger-2 is great for that. And by the way, when you're setting up those scans, the wizard for high resolution is really, really nice to use. And there was one more question, which is from Gokay. Are there stitching problems with the Vantec 500 in low frame sizes, like 128 by 128? How can I import full frame sizes, 2048 by 2048? Well, you know, the stitching is all done on a spot-by-spot basis, on a pixel-by-pixel basis. It's basically going to stitch what it can. So the larger you make the pixel bins, then the more discontinuity there is when the stitch occurs. So definitely I would recommend using a higher frame size when you're doing that. When you import them into EVA, so there are multiple tools actually for looking at Vantec 500 frames. You could have GADS if you have a very old system, or you have EVA, the newer solution where you can actually import the frames right into EVA. If you collected them as 2048, it should bring them in as 2048. If not, if you're having a problem with that, just give us a call here, and our technical service can help you out in terms of getting that correct. But I would recommend using a larger frame size, certainly 2048 by 2048, for doing any sort of stitching. And in terms of overlaps for that detector, what I like to use is at least a 10% overlap. And that just makes sure that we don't have the situation where you kind of have two circles and a lot of missing space. We like to have some overlap. So at least 10%, even better, you could go as high as 30 or 40% overlap to get a nice image set. One note with the Eiger is that it can actually scan as it's going. Nate had mentioned that in the lab segment. And that means that you don't have to actually stitch the frames in post-production. You just pull the data set in, and it's a fully coherent strip of reciprocal space. And we have one more question come in. That comes in. If you do have any other questions, though, make sure to send them into live.events@brooker.com, and we'll get responses to you. And that one is from Cromarty. How does the angular resolution of a 2D detector compare to that of a 0D detector with Pathfinder analyzer crystal? Very good question. So if we start even lower, how does the resolution of a 2D detector? You know, back when I started, we had a high star detector. You know, we had a typical beam that was created by a mirror in that case and pinholes. The limiting factor of that resolution was not necessarily the detector. It was the entirety of the system. There was probably the beam path that was hurting us. The highest star did have a little bit larger pixel sizes, or I should say grid sizes inside, so it didn't give you the best. But if you push that detector farther back, you can get better resolution with it. In that case, though, the beam size itself is what was limiting us. In there, for example, if you measured a corundum standard, you wouldn't be able to see Kappa 1 and Kappa 2 on the 35 peak. But with recent advances in optics, things like this Montel optic and the microfocus source, you can get a beam that is perfectly symmetric in both directions, less than 0.05 by 0.05 degrees in terms of that divergence, and with small size like 0.2 millimeter in both dimensions. And this is small enough that it rivals the resolution that you would get with, say, Bragg-Brentano measurements that are done in that similar setup. So for a classic powder, you can actually obtain resolution where you could start to look at doing something like doing a structure solution. And that would be very helpful if you especially have a small sample, where you really want that concentrated beam, but you want to take advantage of as much information as possible coming off of it. Now, when we're going all the way up, though, to 0D, I would still use the Eiger, but I would bin it into that 0D mode, definitely. And the reason I'd use the Eiger is this. When you have a pixelated detector, you have individual counters on every single pixel. And then that's even backed up by super counters inside of the detector, and that's what gives us this very high dynamic range. And by having high dynamic range, we don't have to worry about flipping in copper absorbers. And what copper absorbers are going to do is they're going to lead to a little bit of inaccuracy in our measurement. They're going to, we define that absorption rate as a single number, when in reality it likely changes slightly over the counting range. But also we're throwing away counts. We went to a lot of trouble to make those counts. We went to a lot of trouble to get that reflection, and then we're going to throw them away with a copper absorber. Well, the Eiger 2 can count the whole thing. And so really the benefit there is that we can count every single photon. But if you really want to narrow it down in reciprocal space to capturing a single XYZ position, that's where that analyzer crystal comes in. It has a very, very narrow focus. That's what it does as an element. It focuses that diffracted area of collection to a very, very small spot. And that is going to give us the highest resolution possible in reciprocal space. So basically, you'd have that Pathfinder Plus, back it up with the Eiger. You have best counting statistics, and at the same time, you have best resolution. And I said that was the last question, but one came in here at the last minute. I am going to answer it. It's from, because of the name, I mean, show me the monkey. Hey. Sometimes when I have two frames, the Pilatus detector, taken of the same sample at different angles, EVA refuses to merge the two. How does EVA know when to merge some frames but not others? Well, when you take those frames, if they're collected in a coupled manner, then it's going to merge them because it knows that it makes sense in reciprocal space to do that merge. On the other hand, if they're collected, say, where you kept the instant angle in one position, then you just moved the detector, well, it understands that there's less coherence in reciprocal space. And so that's why it's preventing you from doing that merge, because it just wouldn't make sense from that practical standpoint. So that's what EVA is doing in terms of logic in the background. So with that, like I said, any additional questions, please email them in. If you do like the broadcast, you want us to keep doing this, remember to subscribe and share this video with your friends, and we'll keep making them. Also, send a thank you out to our veterans. So here in the United States, it's Veterans Day, so thank you for your service. And until next time, let's make sure to keep your signal up and your background down.